And it is a great pleasure to have with us today from the beautiful northern Germany, Gerd Baumgarten, I think, close enough, who studied physics in Bonn and some astrophysics as well, but he decided that the astrophysics was not complicated enough. So he took a challenge of studying the physics of the upper atmosphere. And he did that for his thesis and then moved to Leibniz Institute soon after, where he's working on upper atmosphere and instrumentation as well, and he's an expert on LiDAR. And we are very fortunate, actually, because Gerd was interested to come to Greece to Crete for holidays. In particular, he wanted to actually come and bring one of his cameras that he has all over the world and he just placed it at Skinakas Observatory, looking northwest. So we will have the pleasure to record the beautiful sunsets of the skies in Crete, and he will be able to do the exciting science, and he will tell us all about what happens at around 80 kilometers above our heads.
Yeah.
Very nice to have you.
Thank you. Thank you for the nice introduction. The laser pointer is working? Yeah. So, Noctilucent clouds, we call them also clouds at the edge of space. Edge of space is at around 80 kilometers in altitude. That's where NASA defined the edge of space. So everybody who travels above 80 kilometers is an astronaut. Yeah. That altitude is also covered the camera line. I will come a little bit closer to this later on. Sorry, it's a little bit cut up on the left, but I think we can get it going. If you get it going. Okay, so this is the structure. I thought a little bit where am I from? Why do we do this study? That's part of the things. What tools do we use to study this part of the atmosphere? And actually, what do we learn from it? That's the main intention here. And what detailed questions are we answering? Because you will see it's a very broad topic that I want to present, but I also want to present some details for the physicists. Okay, so IIP is located pretty similar to Crete at the border. We are Baltic Sea Resort. It's a beautiful city, and we're just looking towards the water. So 6 kilometers away from it. It's always green. That tells you that we always have a lot of rain, but also clear skies. So we do have our main building. We have a science lecture hall and the administrative building. Here's our IT compute center. Over there is another hall for building things, and there's a storage. And that's one of the examples of the methods that we use. It's radar. We release radio waves and we detect them. The same thing we do with the LiDARs. We release laser pulses and detect them. We do this at different locations around the world because we want to study different phenomena. Sorry, it's not working all the time. Maybe I do it like this. Let's see if I find the pointer. And then find the pointer. Okay, so we not better either. Okay, so we do study northern Norway, in northern Germany. That's our main facility in northern Germany. And we have some in the southern part of France and in Spain. The camera in Spain we installed 10 years, 15 years ago, and it took us a while to detect some of these nucleus, so showing that it might be increasing. Also, we do studies in the southern hemisphere. We do have some radar instruments and also some cameras looking for nucleus clouds because they are always polewards of a certain latitude. In Europe, we thought it would be poleward of 60 degrees, but that is changing in time, or our detection capabilities have increased. So what are the main topics of IIP? We do exploration of the atmosphere. You can see the atmosphere in this part of the altitude like uncharted territory. There are very few measurements. A while ago, people called it the ignosphere because it was just ignored. We now know that it's important. One example was the unexpected loss of satellites by SpaceX when the upper atmosphere, the thermosphere, extended a little bit due to incoming magnetic forcing. It's not completely answered yet. We do coupling of the mesosphere and the lower thermosphere. So mesosphere is this altitude from 50 kilometers upwards. Thermosphere is the layer from 100 kilometers upwards. Both of them are this uncharted territory, and we need to understand how is energy transferred from the surface of the atmosphere to this upper part of the atmosphere. And we do want to understand what changes are going on. We all know that there's global change, and how does this impact the upper atmosphere? Just very briefly, we are a small institute, reasonably small, 70 staff members, 11 PhD. So you see, we are a research group focusing with some technical supporting stuff. We have 3 departments, and I'm the head of the optical sounding and sounding rocket department, and I will show you a little bit what optical sounding rocket means. But just one step back to the motivation again. Here you can see the sketch of the atmosphere and its circulation. So the atmosphere is a global circulation system. So whenever you, for example, study Noctilucent clouds in the northern hemisphere, it could be affected by planetary and gravity waves in the southern hemisphere. That's what makes our life so challenging, because it's a non-linear coupled system that is rarely observed. We do have some observation techniques like the LiDARs, the radars, the rockets, satellites, but none of them is giving us a full 4D coverage yet. That's something that may happen in 50 years from now, but it's still, right now, we're just digging in some part of the atmosphere. So there are many open topics. Just a recent thing, we had a Leibniz Institute is re-evaluated every 7 years because we get a good funding, but they want proof that we have good funding. So every 7 years, we have to re-prove that we are worth funding, and we just did it in May. That also gave me some material that I can show you. We do research of the atmosphere using LiDARs. This is the smallest LiDAR that we built. Where the pointer is. Okay, this is a cube 1 by 1 meter, and this is a signal it generates. This is typical altitude profile from, let's say, 0 to 100 meters. This is pure air. You just see that the air is decreasing, and all of a sudden you see an increase of the signal again. That increase is due to material that ablates from meteors. Meteors enter the atmosphere, they evaporate and release some atoms. In this case, we use potassium, and then we use a potassium fluorescence. So we excite the potassium atom and we look at its decay. From this, we can calculate temperatures, and also with another system, other channel in the system, calculate how much dust is in the atmosphere, aerosols. So this is a specialty of our institute, that we build these things on our own. Because, as I said, the ionosphere is called because scientists rarely research it. That means that no industry really wants to research it. There are no tools. We need to make the tools ourselves. Okay, this is one example from this that we prepared for the evaluation. The green beam is our typical measurement configuration, typical since October this last year, and the blue beams, these are showing how we want to use the new VAHCOLI system in the future. Okay, that's a picture at night. You can easily.
I have problem finding the place. Anyway, find it here.
Yeah. So you can easily see those by eyes. Just skip over this, technical details. And let's go. I showed you where I'm from. What do we do? How do we do it? I presented some tools. And now I want to show you what do we learn from the Noctilucent clouds. By the way, some people call them polar mesospheric cloud because they're in the mesosphere. So this is way to frame the atmospheric situation. One of the most obvious reasons why we study the upper atmosphere is the temperature profile of the atmosphere. This is from 0 to 100 meter altitude. You have the decreasing temperatures in the troposphere. and then you have the temperature increase in the stratopause, and then you have the temperature decrease due to some upwelling around the mesopause. So all these layers where you have the maximum, that's what we call the pauses: tropopause, stratopause, mesopause. And now, what do you think what happened in summer when the sun is shining on the planet? Well, the lower atmosphere does what you expect. It just gets warmer. The atmosphere receives more solar radiation, but the upper atmosphere gets colder. This coldness is 100-degree colder than what you would expect from radiative equilibrium. And this is because the atmosphere transports energy and momentum from the surface to the upper part of the atmosphere. Usually what happens when the sun shines on the atmosphere, you would heat up the air wants to rise in altitude. And if you have the pole, the air needs to go away from the pole for continuity. But then if you put something away from the pole, the Coriolis force starts spinning up the atmosphere, and you start generating something that we call a vortex. And the vortex is like a barrier, so no more air can flow. But the energy and the momentum from the surface generates friction to this vortex and slows it down, so more of air can flow up and cool it down. So this is one of the what we call the summer paradox. Yeah. So and in this cold atmosphere, in this cold part of the atmosphere, Noctilucent clouds can be formed. And how does that happen? Well, Noctilucent clouds are icy particles. Meteor comes in, evaporates, the dust condensates to very, very small particles that we cannot see. These small particles are then nucleation kernels for icy particles. These icy particles grow due to this cold temperature. And why can you see them only at night? Why do we call them Noctilucent clouds? Well, if you look up into the atmosphere during the day, this would be a typical signal. The signal just decreases with altitude. And that's for a LiDAR. So for each part of the altitude, you would get a certain signal. And if you look with your eye to it, you would just see the integral. You would just see the whole integral of this. And if you look at the signal, you see the Noctilucent cloud fraction is very, very small. It's a very tiny signal. But at night, the Earth provides us with a shadow, and then only the Noctilucent clouds are illuminated. And that's the reason why we can see them at night. Okay, they are observed since, oh, the slide is a little bit outdated, 135 years. Sorry for that. They are impressive phenomena. People have just looked out and saw those, and I must confess, it's easier in higher latitudes because the dawn period is much longer. Here, the dawn period is a little bit short, so you need to look out into the sky exactly 10 minutes around minus 10 degrees solar elevation, something like this. We have to work it out. It's not, we don't know it yet. Okay, we do this because this part of the atmosphere is really difficult to investigate. We don't have many other methods. We do this because Noctilucent clouds are a sensitive tracer. If the cloud altitude rises by 1 kilometer, we know that the temperature has increased by 3 Kelvin. We do have microphysical models that tell us how this is going on. And they show us the dynamics. I will show one example later. And they are needed. And what we need to do is we need to understand their physics. Okay, so one example of what happens to the atmosphere is if so this is a plot that shows you with higher latitude and higher altitude, the distribution of water vapor in the atmosphere. Water vapor just gets lower and lower and lower because solar radiation destroys all the water vapor when it goes up. So that's the reason why it is destroyed. What happens when there is a Noctilucent cloud? The Noctilucent cloud will transport the water vapor from high latitude to lower latitudes and lower altitudes. This water vapor enrichment can be seen, for example, with satellites, but it also allows Noctilucent clouds to travel a little bit further south. That is a process that we need to study in the future. Okay, so much to the theory that the Noctilucent clouds really affect their environment. And well, we also study these Noctilucent clouds because they are interesting on themselves. Here's a microphysical study using radar instruments, the radar I showed you in the beginning. If a radar observed these icy particles, we would call them polar mesospheric summer echoes. Then we also have polar mesospheric winter echoes, which we didn't understand because it was way too warm to have these icy particles, and it is still way too warm. But how did we understand this? We do optical sounding and sounding rockets. We launched a couple of rockets into these echoes. For example, the radar observed one of these echoes. We do measurements with winds because we need to understand the dynamics. Then the temperatures by the LiDAR. So we combine all our efforts to get a really short scale snapshot. But to understand the physics, you really have to use rockets sometimes. Although it's not covering the whole globe, it's very short, but it's one of the only tools. But I have to mention that this is a community effort, I would say. We have many institutes working with us on this. Okay, let's have a look at the history of sounding Noctilucent clouds with LiDAR and laser. So it was proposed already in 1887. People thought, okay, let's just put up a lamp and shine into the Noctilucent clouds. People tried it in the 1960s. Careful efforts didn't work. And then roughly 100 years after the idea, the first technical realization was done. So you see, it's a challenging thing. I would say we have now the time for really good Noctilucent cloud studies because our technique has improved a lot. I showed you the rocket launch. This is the setup of a LiDAR system that we use. The LiDAR is on an observatory on a hill or a mountain, a 400-meter high mountain in northern Norway. Contrary to other observatories, we have the telescopes 2 times 1.8 meter inside the building because the weather is so crappy in Norway sometimes that you need to protect all of this. We had domes blown away, things like this happened before. So, and then the building was built, yeah. We do LiDAR measurements straight up, for example, and under a certain angle to hit the same volume as a rocket does. And this is how it looks. I thought I'd make some relaxing slides. So this is how it looks from 5 kilometers away or something like this. You see there's a little bit of aerosol in the air, and then all of a sudden the laser gets really bright. Other than that, this is pure air scattering. And this is now a little bit more scientific, understandable altitude signal from the atmosphere. If you shine light into the atmosphere and then you measure, for example, how does a LiDAR work? Well, a LiDAR makes 3 meters of light and sends it to the atmosphere. We make this 3 meters, and then we just record the time when we launch it, and then we every 10 nanoseconds we record how much light we get back from the telescope, and then we store this data. And that's how we generate an altitude profile. That's the light detection and ranging LiDAR. Again, you see the Noctilucent cloud is really, really small compared to the signal you get from the lower part of the atmosphere. So initially, we did block our telescope, our electronics mechanically to protect them from the light from the troposphere. When we had old detectors, with new detectors now we can just use all the way up. And just the efficiency of our system, I think no one would build a system like this using the efficiency chart, because 90% of all the photons we generate just goes out into space. 10% is scattered below 20 kilometer, and then 0.01% is scattered from the clouds that we're looking at. So it's really, really inefficient. We scientists always like challenges, so we took the challenge. We have just bought new lasers that have more power. As I said, we have 2 telescopes, 1.8 meter diameter, and we do have 2 narrowband filters because Noctilucent clouds at high latitudes appear during daytime. So we do use 1.8 meter telescope, look into the sky during daytime, and we need to find this little light that was generated from the laser, and we use very narrow spectral filters This is shown, for example, down here. This is our detection bench. We detect many colors, 3 colors, no, 5. And we have a daytime filter, so the sunglasses of the LiDAR system are fixed baseline eternons, 2 of them now, 1 of them now, with a bandwidth of 4.7 picometer, so really narrow band, I would say. Okay, this is just a sketch. This is a person here next to the 1.8 meter telescope that where you can see how the beam is going out. Okay, so technical challenge was taken. We managed to get it going. This is now 5 days in a row or 7 days in a row. This bluish thing that runs through, these are the Noctilucent clouds. You see how they are going up and down. You see many waves in those. And these small waves are the waves that were needed to make the atmosphere cold. So the Noctilucent cloud on one hand are generated by these waves because the waves make the atmosphere cold, but they also allow us to study them. So that's a good combination. Okay, this is too much. That's how a LiDAR works. Now, what can a LiDAR do? We can, for example, extremely precisely measure the altitude. This is now for 135 years, the altitude of Noctilucent clouds. And you see why we took this challenge, because it's the only source of information we have from the upper atmosphere that gives us data back to 1800 something. Of course, life is not as easy as it thinks. I will show you a little bit in a minute how the altitude was measured in the old days. Today, you see all these green dots measured by the LiDAR scattering around a lot, and that's again due to the waves. So what we have learned is that the atmospheric waves are really, really prominent in this altitude region, and Noctilucent clouds show them nicely. We do think that we can start to measure the trend now. We have 20 years of data, and we have a decrease of Noctilucent cloud altitude by, let's say, 20 meters per decade. So 0.2 meters per year. A technical challenge. If you insert a cable that is 2 meters longer because the electronic moves somewhere else, you're changing this. So we always need to be very careful whenever we do updates to the system that we don't destroy our long-term records. This is now coming closer to where we are here. This is now observations from our institute. We're looking to the Baltic Sea. A couple of these cameras. And here the camera was looking straight up. And you see wavy structures. At the same time, down here, we have the LiDAR signal. And I'm showing this because I think this is also our progression. We firstly thought we can do this measurement only in high latitudes. And now we have upgraded our LiDAR and the cameras, and we see that we can do this complicated measurements in and lower latitudes. And you see how the atmosphere goes up and down, very well shown by Noctilucent clouds. All these wavy structures.
This is in the mesopoles.
Yeah, that's at the mesopoles. So we measure the altitude of clouds with a precision of 10 meters, 20 meters at 80 kilometer distance, just by measuring the one time of light. And why do we do this again? One of the theoreticians that we work with, he said this is the only tracer in the whole solar system that where you can do this, because you have the LiDAR that tells you how it's moving, and you have these cameras, and you can combine the horizontal information and the vertical information in real life, not only by modeling. There are many models. Yeah, sorry, it's an automated video, but that's how our current interest, where our current interest is. I told you that it's also used as a tracer. We want to use this old data and just redoing what the people have done in the past. We have 2 cameras, dual camera things. Cameras located separated by 30 kilometers. You look into the sky at exactly the same time. You pick a cloud feature. You see it from one camera. You take the cloud feature from the other camera. Then you compare it to the stars, and then you know how much Oh, then you can calculate the altitude to make the long story short. You can do this with different features within a band. This band that you saw in the picture. And for us, it was very interesting that it's changing in altitude quite a lot. Not sure that I can see this here. Compared it to the LiDAR measurements, and they seem to agree. Okay, so yeah, that is the point again. 130 years of this data.
And are you able to distinguish between temporal and spatial variations? Because sometimes the signal jumps all of a sudden. That must be spatial.
Yeah, that's exactly. Yeah, I could have another presentation on that. Okay. Because it's very interesting for us to, for example, I just showed these examples with the wavy things. If you have a camera, a LiDAR, and a radar, then you can see how the motion of the layer is going up and down. The camera shows you that it's blown by the wind. So yeah, we do, but it's not published yet. So yeah, that's one of the most challenging things. The previous slide showed you publication we did last year. Last year, when it was accepted, we thought, oh, this is an extreme event, it never happens again. And then in the same year, when this one was published in Spain, we got this is even a Spanish TV picked it up and showed some of our frames that we capture at the Cala Alto Observatory. I'm not sure if people know it, but there we have a camera since quite a while. And that's the statistic I showed. I said it took us 5 years to get the first Noctilucent clouds, then 5 years of nothing, and then all of a sudden the Noctilucent clouds are picking up. So that was the point when I sent an email. Yeah, let's do a Noctilucent cloud camera here, because you see people are just looking out in the sky. They see this, wondered, and interested, and we already have the answer. So we just need to show them that this is happening throughout the whole atmosphere. And now, what do we expect? We also do Noctilucent cloud long-term studies, but then you need to have more models. We do have models, the increase of CH4 and the increase of CO2, and we see that, for example, CH4 increase makes the Noctilucent clouds much brighter. I don't want to forget about the details here, just to see that one curve is going up. Noctilucent clouds are getting brighter because methane is released. Methane rises in altitude, comes to an altitude where a lot of Lyman alpha radiation is available. Lyman alpha dissociates methane, and then methane oxidizes to water vapor. And the water vapor is then making the Noctilucent clouds brighter. So it's atmosphere. It's always things like this. But the funny thing is, if we increase CO2, brightness is not changing, but the Noctilucent clouds are decreasing in altitude. That's because we have more infrared radiation coming from the stratopause, so the stratopause region gets colder, and then the whole atmosphere sinks down. Okay, so these are the things I want to show you. So in real life, a Noctilucent cloud looks more complicated than this, but this already gives you an idea about the planetary wave activity. Usually we have winds from the east, yeah, so this way around, that's the vortex, winds from the east. And then in this wind from the east, you have waves traveling that make these blobs. These patches of Noctilucent clouds. You see they were distinct, separated 100 years ago. Now they seem to be spread more. Yeah, still you have times when you have no Noctilucent cloud, but once you get one, it just gets brighter, so it gets more likely to see it. And in future, we expect that this is increasing much more. Okay, we use the scenario that took most of the methane increase, yeah. But that's how scientists work. We want to see the worst case. And now we're trying to study what does it do to the chemistry of the atmosphere. One thing is that it affects the water vapor transport, but the other thing is also that it has a different transmission, especially in the UV. So we could have less UV radiation in the ozone layer. That makes less or more ozone. I forget it now. So these are the things we are looking forward to. And why do we do it? Why do we study the southern part, I want to go back one step. Yeah, you see this model never makes the Noctilucent cloud south of Germany. We know there are Noctilucent clouds, so we know there's something wrong. And this is the model that does the best job in making Noctilucent clouds at low latitudes. We have ideas already what it is because the lower atmosphere transports energy and momentum upwards. But this is small scale processes. These are small scale processes. I told you that even satellites having global coverage, they measure sparsely because the satellite needs time to travel around the Earth. And LiDAR is located only at one place. So there are many things undetected in the atmosphere yet. And these are gravity waves, for example, and I call them the dark matter of the atmosphere because we know they are there. We know they have a big impact, but we just don't know how to observe them regularly. We have some ideas. I showed you some movies of Noctilucent clouds already. This is a typical picture, a little bit zoomed in. You can see nicely waves. These are scales of 20 kilometer horizontal wavelengths. And then we have small scales here. And we do have waves and turbulence. And that's exactly the process we want to study. How does a wave transport its energy and momentum to the atmosphere? And you can see it here. There's a Kelvin-Helmholtz instability. And these are all secondary structures generated. And this kind of observations give us the possibility to give scales to the process because usually these DNS simulations, they are scaleless. You can do any scale you like, but here you know the horizontal scale is 20 kilometer, the vertical scale is 10 kilometer. So we can work it out and give things to input to the modelers. And I think this is just a detail how we do it other ways. I think that's about what I wanted to show you. I have a little bit of outlook. The research questions I have here is how do Noctilucent clouds look like? Do they always also have this waves? Do they have this these small scale waves interesting at, as I said, do they have waves? In Spain, we always have this funny thing. We have one Noctilucent cloud, no Noctilucent cloud, one Noctilucent cloud in one season. It's always a 2-day separation for all of the cases we have. So this is hinting us to a 2-day planetary wave, which we don't expect. So that's one thing. And then long-term goal, we want to run the camera for a while. Do we see more of them here? Do we see any of them? I mean, that's the first thing. And do they increase in brightness? And then that's outlook. This is from last night. This is the camera that we installed. You can see, I hope this is Santo. So I guess this is Santorini. Would that be the next? Yeah. And we probably want to move the camera a little bit more to Santorini. The time when Noctilucent clouds, -36, 4, 5.
So these are measurements from yesterday.
From yesterday, yeah.
Oh.
Yeah.
We should send us the video.
Yeah, you will get that. That's no question.
There are some structures traveling there. What are
these are tropospheric clouds. These standard clouds. So this was just a full scale. It's a high resolution camera, 34 megapixel. So and we probably want to look a little bit over Santorini here. So that's something I want to work out in the next days. And then there was maybe one more video, and if not, then I can show it like this. I wanted to show you when. I wanted to show you where the camera is mounted. That's not gonna work. Which video? That's gonna work. So that's also from yesterday. And the camera is it's really small. I mean, it's nothing impressive. But I think that's what I learned with the camera. Yeah, we decided to thought let's have a look at the sunrise, so I can show a nice movie.
Okay, but you turn it.
Because we were a little bit late for the sunset. Yeah.
Okay, but normally you would point from the sunset.
Maybe more towards Turin. Let's see. We did have another camera looking to the sunset. Not high resolution, and I want to compare it to. Yeah. Okay. By the way, we have installed a new camera that hopefully doesn't work. These are these standard DSLR cameras with high resolution, and in Spain we need to replace them once per year. But this is a new one which works shutterless, and I tested it a lot. So because we already broke a lot of these cameras, just shutter gets broken and it's reinstalled. Yeah. So and yeah, my plan is to go up there later to have another look at it. Good. Now I'm done.
Okay, so there are a couple of questions online from Vassilis and Davis. The first one, do you want to read them or should I?
Maybe. Or they can say it, maybe.
Yes, so please read them so that they can.
Shit. It's the other way around. That's always confusing. So we want to get rid of this, and then we want to get rid of this, and then we make this participants.
Hi, Gerd, can you hear me?
Yes, I can hear you.
So I can read my questions. First of all, thank you very much for this impressive talk. It was a great talk, and happy to see these measurements for Noctilucent clouds. And my question was related, first of all, is a process-related question on the stratosphere-mesosphere coupling. Do you believe that there is an interaction between these two layers that may be stratosphere, because we experience a lot of changes in the stratosphere lately, you know, about the ejection of volcanic ash particles or the new mega fires that are ejected directly, smoke and water vapor in the stratosphere, how this affects mesosphere. Do you believe that this is feasible?
I think there's a strong coupling between the stratosphere and the mesosphere, mostly due to those waves. Some is also due to the radiation, because the atmosphere then shrinks. I'm not sure that the aerosols in the stratosphere have a big impact on the mesosphere yet, but I must say that I'm a fan of stratospheric aerosols too, because since we optimized the LiDAR for mesospheric measurements and stratospheric aerosols, we can resolve really small scale structures that people have not seen before.
Yeah.
So
they're
very important, but more for the altitudes below the stratospheric aerosols.
Yeah, this was what we thought on the troposphere as well, that aerosols do not affect, you know, the high level clouds, cirrus clouds, for example. But now we realize that even one particle in 1 liter can provide a nice sized nuclei to have the development of a cirrus cloud in these regions of 12 kilometers, let's say. So this is why I asked, but of course it's a long shot, I understand. My second question is related to the satellite LiDAR datasets. Have you ever exploited Calypso or the new Aeolus sensor, for example, for wind measurements, and how these sensors can deliver information on your work? Because, you know, you don't have that attenuation of the signal when you look from space, so you may get even better retrievals.
Yeah. So what is the polite answer? I applied for a RDM Aeolus validation project in 2005 because we want to use and then when Aeolus was ready to launch, we lost the interest because we realized that this lower part of the atmosphere, Aeolus is not providing the higher part as it was scheduled.
True. You're correct. But Calypso does, right?
Calypso is very interesting, comparing with polar stratosphere clouds. But, yeah, but you see, I'm struggling here because the main focus of our institute is this MLT 50 kilometer upwards. We do make these observations, and I like to call them beautiful, but we don't have the manpower to work on the data much. We just applied for a new project to get more people to work on it, but yeah. It's not
Understood.
in focus. Yeah.
Mhm. And a final question, I don't want to spend much of your time on that, but I saw that you use the Alomar LiDAR, and then there is, I'm sure you are aware also of the Polynet network of Tropos in Leipzig, right?
Yes.
There are LiDARs all over the world, yeah. And these LiDARs can provide multi-wavelength measurements. Have you ever thought of using these spectral dependencies or the polarization returns to better characterize Noctilucent clouds?
I want to give you a thank you for this question because that is the specialty of the Alomar LiDAR. We do 3 color measurements. At night, we also do this multicolor with 2 additional Raman wavelengths. And you need to have these 3 wavelengths to calculate the sizes of the icy particles, which we did. I didn't show it here. It was just too much. And we also did the first depolarization measurements on Noctilucent clouds that proved that these and indeed icy particles. Earlier, the modelers were just assuming they are spherical. It has no physical reason. It was just assumed. And yeah, so yes, we do depolarization and multicolor measurements, but not routinely because after a while, this new satellite Sophie, it delivered much better information about the.
Yeah.
So yeah.
Yeah.
We saved.
Yeah, I understood. Thank you, Gerd, very much. Just for your information, I will send you an email because we have recently developed a new LiDAR called VAHCOLI that actually deploys both polarization channels in the linear polarization channel and the circular one that can operate also an elliptical one. With this combination, you can even study the orientation of the ice particles, which might be of use in your studies. We use that in Sirius when we found out that they are horizontally oriented. So this affects also the radiation, you know, the propagation of radiation through this layer.
Yeah, maybe, yeah, sounds interesting. Just one thing to keep in mind is the depolarization of Noctilucent cloud particles is in the order of 1%. 1% only. Because
only 1%. Mm-hmm. Okay, okay.
Because they're
this
so
is
small compared to the wavelengths. Yeah.
This is very challenging. Yeah. Okay.
Yeah.
Okay. Thank you. Thank you.
Yeah. Welcome. Okay. Shall I try to read this?
I think those were all the questions.
Okay. Good.
I have one.
Yeah.
I'm trying to understand, to picture the geometry of these clouds. You have this picture there. So I suppose that these are sheet-like
exactly.
clouds, right?
Yeah.
That form these gravity waves, which are ripples.
Yeah.
Or are they actual density enhancements? So do they represent corrugations like the curtains, or the density changes and we see them like that?
Again, this one. Okay. Anyway, so this wavy structure here,
Right?
that's probably just these are high frequency or medium frequency wave. The sheet is just pushed up and down by vertical motions.
Okay.
So this that's what we still call waves. Also, it looks like ripples. Ripples are these small things here. Sorry for this small thing. They are generated by turbulence, and they are often aligned perpendicular to this initial floating, and they are indicators for turbulence or decaying waves. Yeah. And the question is, are they density enhancement or not? I think it's not density enhancement. It's just pushing the layer up and down, and then you have a very shallow angle looking through it.
Right, right.
Yeah.
So, where does what's the direction of the flow?
Typically, for this picture would be like that, from the northeast.
So these waves then are usually formed perpendicular to the flow?
No, these are traveling often against the flow. These ones are very slowly traveling, because then they seem to get more pronounced. They're slowly propagating, so you can easily.
So they propagate upstream.
Yeah.
Wow.
Then when a wave comes from the surface and it travels up in altitude, its amplitude is always increasing. That's because the energy stays constant, the density decreases, so the amplitude is increased. So sometimes when a layer moves up a little bit, then the amplitude gets too big and then it just breaks. That's when these ripples are generated often.
Can you reduce the wavelength from there? Is this compatible with gravity wave?
Yeah, on many of these slides I didn't show. Yeah, that's one of the plans, and the wavelength is the important thing. Yeah.
Propagation also. So that's the mechanism, gravity waves, you think?
For making
Something
these
else?
structures, yeah. The long-term fluctuations from day to day or within the day, these are tides, solar tides mostly. I think 30% we can attribute to lunar tides. We worked that out too. So, but you know, there's never a direct mechanism. No? Atmosphere is always, I mean, solar tides are not generated or not input at the Noctilucent cloud altitude, they're input at the stratopause, and then the stratopause has to transmit these waves to tides.
The tides are much stronger than gravity waves, therefore we must be seeing diurnal variations, for example.
Yeah.
Also planetary wave variation, 2-day waves, and so on.
Yeah, exactly.
Also, it's the atmospheric dynamics that define all these. There are no instabilities in other words involved in there, isn't it?
There are no instabilities.
Well, some atmospheric instabilities, possibly that could generate those waves.
Yeah, I'll try to show this one figure here because that addresses all scales. This one. So this picture here, 24 hours, so one day. And you see on that day it was just around noon. The next day it comes in the morning hours, more or less, but again around noon. Nothing on the third day. Then you see changing, moving up and down. So the day-to-day variation is mostly due to the tides, but the tides are themselves not as well defined or reoccurring. They're intermittent, we call it. Some days you have it, some days not, and that depends on winds and the stratosphere probably. And yeah, so I forgot where the question came, what you asked for.
Anyway,
yeah. But you see, they are affected by all these waves.
Yes.
That's, yeah.
Yeah. So I have a question about the. You mentioned that during the summer, the temperature decreases by around.
Yeah.
Right? So can you repeat why?
So
What's the difference between summer and winter and causes this decrease?
So in summer, let's say the Earth here, sun shines on the southern pole, brings in a lot of radiation. So the radiation wants to push the atmosphere up. It just gets warmer and wants to push it up. And then the atmosphere rises. When you have atmosphere going up, then it always gets colder. 1 kilometer makes you roughly 10 degrees colder. So it's a really strong impact. But then, and that's why in the summer pole you would expect a cold temperature. You put in energy, air rises, and it gets cold. But as I said, this is the paradox is in the upper atmosphere it gets cold. The paradox is the air cannot flow away from the pole usually because you would get this circulation going, and for this you need the gravity waves to stop it. In winter, it's the other way around. You have no solar radiation. Air wants to go down. Downward motion heats the atmosphere. So that's yeah. That's the simple picture why the summer is colder, air goes up. Winter is warmer, air goes down. Yeah.
And another question is, if I understood correctly, you mentioned that this reality of these clouds decreases as a function of time.
Yeah.
But I don't understand why.
The stratopause region has more CO2, and the CO2 radiates more infrared radiation away. So you cool the stratopause region. If you make the air colder, it shrinks. So the whole atmosphere sinks down, and the altitude of the Noctilucent cloud goes down.
Okay. But do you expect that this is a monotonic behavior, or is it that fluctuating
This is
behavior?
our simple assumption was that we ignore all our model. You need a model for this. There's no way to.
Yeah.
So the model has just CO2 increase and methane increase, but we keep the tropospheric dynamic. So the weather we keep constant. in time, what can happen is that more energy in the troposphere makes more clouds make more radiation. You heat up the stratopause again. So I must confess, I don't know what happens when you make a real atmosphere. We made a simple atmosphere and then the cloud altitude goes down. And that seems to fit to the observations. But you have to see, we have a trend of 20 meter per decade, but we have a year-to-year fluctuation of 1 kilometer. So the weather in the troposphere could easily go up. So yeah, I can't tell you. Yeah.
One last.
Gerd, if I may, one final question. What we do in the troposphere, sometimes we're using, aerosols or clouds as signatures that we follow in order to explain and translate dynamics, to retrieve information for dynamics from that respect. So what we do is, since we have all these vertical profiles from Calypso, for example, and future sensors that are planned for vertical profiling of aerosols and clouds, we are assimilating in models. I'm sure you heard about that. ECMWF is doing a lot of work on that. Mm-hmm. And then you get better dynamics, you get better representations from models. And from what I saw from your simulations, you showed something about the pole, the North Pole, and that this is not accurate enough according to observations, is how to utilize Calypso and use data assimilation in order to have better representations. And then to conclude maybe on physics. So this is maybe a way that you could consider in the future. I don't know if your community do that, but for sure in troposphere we're using it a lot.
Yeah, to be honest, what we do is we take ECWMF data, which hopefully includes this effects, but you're totally right. Having a good lower atmosphere is very important for understanding the upper atmosphere. Mm-hmm. I think that is the main message I would see here.
But also for the upper, you can even improve and optimize the model runs using data assimilation, constraining with observations. I mean.
Yeah.
Mm-hmm.
No, that's true. Yeah, that's a good idea. Okay.
May I have one last one?
Yeah, one last question. Yeah.
So you saw this transition to turbulence, right? For when the amplitude of the waves increases a lot. You must have precision measurements, right? So you must know what is the threshold for instability. So how nonlinear should these waves become to get this transition? Do you have numbers? I mean,
That's a good question. I don't have any numbers in my head now. I must confess, we do right now. It's the uncharted territories. We are looking at instability types and try to define different types and how we evaluate them. At very single cases, we measure the horizontal wavelengths, vertical wavelengths, and then we can provide the scales. But it's one case and all the cases are different. So we need to have statistics before I can give more reliable numbers there.
Yeah. But it's impressive because the Reynolds numbers, right, in this altitude must be huge.
Yeah.
And yet these are stable waves until they become highly nonlinear, right? Yeah. And they break up.
Yeah. The viscosity is like honey in this part of the atmosphere. It's very stable usually. Yeah.
Those of the pictures don't seem breakup. Just very nice.
No, there were breakups when the altitude was very high.
I can show you this one. This is Kelvin-Helmholtz instability, and can look inside the Kelvin-Helmholtz instability. Here, this one.
Right.
This is the Kelvin-Helmholtz instability. It looks like waves, but these are structures generated in the turbulence.
Right.
And from this separation, from this non-wise separation, we calculated some scales. Yeah. Okay. And that's the uniqueness of this tracer, because it's a very thin sheet, extremely thin sheet. So, but these observations not many of them, but you need to find the correct space and time, and then you need to spend a lot of time on getting these dimensions right.
Yeah.
LiDAR in one sense is very easy because you know the speed of light, you record the photos. But here you just look into the sky, you have some stars, you can align to it.
Yeah,
So-
projection effects.
And I would like to have this in 3D with 2 cameras. So that's what we are working on.
Thank you.
Okay.
Thank you.
Yes,
Yeah.
thank you.
Thanks.